In this video, let us try to understand a term what we call a equipotential surface. So, we have understood what is potential. So, whenever there is an electric field, we can define at a point electric potential. So, once we define an potential, let us try to understand or get a picturize what is we call the equipotential surface. To make the work simple, say let us imagine there is a point charge say Q. Now, if you think of this point charge Q, and if I think of a point say A here, say at a distance say from this point charge at a distance of say R, say at a distance R from the point charge, say I will take this point A. Now, at this point potential V is equal to 1 by 4 pi epsilon naught into Q divided by R. So, for a given charge, that is source charge, potential is inversely proportional to R, or else I can say purely it depends on the R. Now, if I can think of a point, say another point, say B here, say B at the same distance, say at the same distance of say R, then I will say that the potential at A and potential at B is also same. Similarly, if I think of another point, say set of points say C here, say at a distance of say R, now here also the potential remains same. So, I can think of a points A, B, C, D so on, wherein the magnitude or the potential due to this charge remains the same. When I draw it on the blackboard, if I join all this point, so what I am going to get? I am going to get a circle around this. So, a circle around the given charge. So, on this circle, what you will come to know? The potential at every point will be the same. This is on the board, it will circle will get. Now, if I take one more distance, say potential at a point, say at a distance of D. Now, I can imagine a circle, another circle with radius as a D, where on which every point the potential will remain the same. But potential here, say if I take it as a V1 potential on the first circle, on the second circle, potential on the V1 is not equal to potential V2. But whenever you think of the points on this circle, the potential is V1. When you think of this bigger circle, potential on this circle everywhere remains the same. Now, let us think in a three-dimensional space. That is, imagine if there is a charge here, say imagine if this is a charge, I can think of a sphere. When I think in the draw in a blackboard, it becomes circle. When I think of a charge in a free space or the space, three-dimensional space, it becomes a spherical surface, wherein at every point on the spherical surface, the potential will remain the same. Or else, for any given charge, say if I have a point charge, you can think of, if there is a point charge here, say plus Q, you can think of a sphere around this. Say you can think of a sphere around this, around the charge. You can think of a sphere. What sphere this? The property or this sphere is such that every point on the sphere, if I take this as the center of the sphere, on every point on the sphere, say I take a point A here, I take a point B here, I take a point C here, D here, everywhere on the surface of the sphere, the potential remains the same. So, this type of surface on which potential at every point remains same, then I can say such surfaces are nothing but equipotential surface. So, what is an equipotential surface? A surface on which potential at every point remains same. Such a surface I can call it as an equipotential surface. If the I think of a point charge, the equipotential surface comes to be a sphere. Now I can say the shape of the equipotential surface for a point charge, say isolated point charge. Isolated point charge comes to be a spherical, or else spherical equipotential surface for a given point charge. You can think of any smaller sphere, or else you can think of any bigger sphere. Say if I have a charge here plus q, I can think of any number of spheres. This is not a circle I am drawing the sphere one, say one sphere, another sphere with a slightly bigger radius. I can think of one more bigger radius. You can think of an infinite number of this kind of concentric spheres. These surfaces will be, say if I take this surface potential, let's say A, this on the surface this be B, this is C. So VA is not equal to VB, not equal to VC. This is very important to note. So on this sphere, potential at every point remains same. So I can say this is one equipotential surface, this is another equipotential surface, so this is the third equipotential surface. So you can think of any number of equipotential surface. So altogether, if you ask what definition for the equipotential surface, what is an equipotential surface? So a surface on which potential at every point remains same, that is called an equipotential surface. For a given point charge, the surface comes to be spherical. Let us slightly try to elaborate this, try to understand this. Say think of the positive charge. Now if you think of a positive charge, say plus q, we know that the electric field radially diverge outside from a positive charge. If I write, how do we draw the electric field lines? We draw the electric field lines like this. Electric field lines are imaginary lines, they are not the solid ones. It's an imaginary representation to show the direction of electric field. So we will say the electric field due to a positive charge, isolated charge, it diverges radially outward. So if you think of a positive charge, say this electric field now, what are equipotential surface? Now if I think of an equipotential surface, how the equipotential surface? Equipotential surface is a sphere with the charge at its center. So if I draw, this will be my equipotential surface. Now if you look at this equipotential surface and the electric field, this electric field and the equipotential surface, now you will see that you draw any number of electric field lines like this, you will see that at every point the electric field direction or the electric field is always normal or perpendicular to the surface. So the electric field is always normal to the equipotential surface. So this is the radial one, electric field line will come along the radius of this equipotential surface. So I can say it is always perpendicular. Say anywhere you draw this, you will see the equipotential surface at every point is perpendicular to the electric field line. You think of this positive charge, or else you think of the negative charge, say minus q, wherein what we will do, we will take the electric field lines radially inward instead of the outward direction, we will take it as a inward electric field. This way we will take. You draw any number of electric field direction, that is electric field lines. If you draw this, what the equipotential surface is nothing but a sphere around this. So, we will see that this surface is normal to the electric field line. So, the first characteristic or property what it comes, equipotential surface is perpendicular to the electric field or is normal to the electric field direction. So, this is one important point to remember. Now, keeping this in mind, let me think of what will be the equipotential surface if it is a electric field line due to, instead of the positive isolated charge, let me consider a uniform electric field. Say I will think of a uniform electric field. I do not know what is the source or is due to what electric field is generated, but here there is electric field which is uniform. So, uniform electric field. Now, what will be its equipotential surface? Now, by taking this idea, the equipotential surface is perpendicular to the electric field direction. If this is the electric field direction, then if you can think of a surface which is normal to this, then that will be a plane surface in this way. So, you can think of the surfaces, plane surfaces like this. So, just like if I keep my palm like this, the electric field lines will pass through my palm, that is passing through this, make an angle of 90 degrees, so perpendicular. So, I can say this surface A, this surface B, or say this surface C. These are all nothing but the equipotential surface. Does not mean that potential at A is equal to B, VA is not equal to VB, not equal to say VC. But potential at every point, say if I think of this point, this point, this point, this one, anywhere on this plane, potential will remain the same. So, this is an equipotential surface, this is an equipotential surface, and this is an equipotential surface. Now, when the word itself says the equipotential, say again we will come back to this. If I think of this point, say I will think of a point R here, say I will think of a point P here. Now, so if I take say another test charge, think of a test charge or else a unit positive charge, say let us take a unit positive charge, say +1 coulomb. Let us try to move this from point say R to P. Now, in the earlier discussion we have said the work done in moving a charge from one point to another is nothing but the potential difference. Now, here it is an equipotential surface. Since it is an equipotential surface, what happens? Potential at P is equal to potential at R. So, if Vp is equal to Vr, then potential difference is 0, that is Vp minus Vr is equal to 0. If Vp minus Vr is equal to 0, then the work done must be equal to 0. Why? Because work done W is equal to Q into Vp minus Vr. Since Vp minus Vr is equal to 0, work done goes to the 0. So, this will be the second property of the equipotential surface. First one is equipotential surface is normal to the electric field direction, and the second one, work done in moving, you say unit positive charge or any charge, work done in moving a charge from one point to another is always equal to 0. In another word, you can say potential difference between any 2 points will be equal to 0. This in reverse has a confirmation or the argument for why the electric field must be normal to the surface. If electric field is not normal to the equipotential surface, that is, say imagine if an electric field comes like this. If an electric field is not normal, let us assume that electric field is this direction. Just if it possible, let us assume that electric field here. Whenever here there is electric field, then you can have its own components of electric field. So, this electric field can be resolved like this. When we can resolve this, there is a component of electric field along this direction. Whenever there is a component of electric field along this direction, any charge which tries to move in this direction will experience a force. If it experiences a force, then we have to do some work. If there is a work done, then there will be a potential difference between point say A and another point closely lying point say B. Now, if a component comes along this direction, it results in a work done which generates a potential difference between 2 points, but which cannot be true. Why? Because the surface itself is an equipotential surface. So, if it is an equipotential surface, then electric field must be normal to this, so that it won't have any component along the surface of the potential. That is why electric field is perpendicular to the equipotential surface. So, the two important point to note, that is, the first one is it's how what is the direction of electric field with the surface. Second one, what is the work done in moving charge from one point to another charge. For a point charges, the equipotential surface will be concentric spherical in shape, or the concentric spheres will be the equipotential surface. If it is an uniform electric field, then the equipotential surface comes to be a parallel plane surfaces. You can think of different arrangements of charges. So, you can think of say a dipole. Now, the equipotential surface, say for an arrangement of say dipole, two equal and opposite charges, say one is plus and another one is minus, separated by a small distance. Now, if you think of the equipotential surface, say it is a spherical one, slight rearrangement of sphere takes place, and this side there is a slight compression and this side just pulling. It is not an elliptical in, almost a spherical only. So, this diagram is drawn by taking the direction of electric field first, then you draw the normal surface over to that, and that you will get this. Similarly, for an equipotential surface, for two positive charges lying very close, so this will be the shape. Here the potential surface comes closer and here it goes separated one. So, this is for the two positive charges and this is for the two for a dipole one. After understanding what is an equipotential surface, let us try to relate electric field and potential. So, let us have what is the relation between field and potential. Now, for that, let us assume in a simple case where there is an uniform electric field. Say, think of a uniform electric field, say directed this way. Now, let us consider two equipotential surfaces. We can think of say an equipotential surface. Since it is a uniform electric field, equipotential surface will be a plane surface. Say, let us take this to be a point, say A, surface A, and let us take another equipotential surface, say B. Let us take the distance between the two equipotential surface. So, let us take it as a delta L, the distance between the two equipotential surfaces. Now, let us consider 2 points. Say one point on the equipotential surface, say B as R, and let us take one more point on the A as a B. Now, with the definition of potential difference, let us try to relate the potential difference and the electric field. Now, let us assume or let us consider a unit positive charge which is placed say we try to move a unit positive charge of say plus 1 coulomb from the point R to the point P. Now, this is the electric field direction. Whenever I move the charge plus 1 coulomb from R to P, that is a point on one equipotential surface to another equipotential surface, then I have to do some work against the electric field. So, I am moving the charge in a direction opposite to the electric field. Say, let me take here the potential on the first equipotential surface to be V, and this let us take it as a V plus delta V. Now, what is the work done then? The work done, say work done in moving unit positive charge, that is plus 1 coulomb unit positive charge from point R to P. So, let me take the work done W is equal to F to delta L. Why F? Because F is equal to Q into E. When Q is equal to plus 1 coulomb, then F becomes equal to E. So, I can write this W is equal to E delta into L. So, now W is equal to E delta into L. If you write in vector form, then I can write vector E into magnitude of the vector. So, altogether I need magnitude of vector E into dl. Now, let us take this to be 1. Now, what is the potential difference between this? Say the potential difference between R and P, I can write the potential difference as say delta V is equal to potential at the final point, that is Vp, minus the potential at initial point. So, I can write this as V minus V plus delta V, that is equal to V plus delta V. This becomes minus delta V. So, this is the potential difference. Now, what is the definition of the potential difference? Potential difference between any 2 points is nothing but the work done in moving a unit positive charge from R to P. So, this work done is nothing but potential difference. So, I can write it as therefore, W becomes equal to the delta V. That implies work done is nothing but E into delta L is equal to the potential difference minus dV. Now, that is equal to magnitude of E equal to minus of dV by dl. Either we can stop it here only. The relation I can say the magnitude of the electric field is equal to negative. Whenever something is divided by a distance, we use it as the gradient. So, here you can say electric field is equal to negative potential gradient. This delta V is nothing but change in voltage with the change in distance, or else I can say change in potential along a normal direction. This is delta L. So, this is equal to E is equal to negative of delta V by delta L. What is given in our NCERT book? Again, one more step is added. They have taken that dV itself is negative. dV itself is negative in the sense, in the direction of the electric field, potential will decrease. Why? Because what is the definition of potential at R? Definition of the potential at R is nothing but work done in bringing a unit positive charge from infinity to this R. So, obviously, what the work we have to do to bring a unit positive charge from infinity to R, is slightly lesser than what work we have to do it when we bring a unit positive charge to the P. That is why potential at R is lesser than the potential at P. So, obviously delta V should be negative. So, delta V is already negative. You can write that implies magnitude of A is equal to minus becomes plus. I can write delta V by delta L. You can stop it here also, you can stop it here also. That is only the negative sign convention or the sign. So, what this mathematical expression reads that electric field is the negative potential gradient. In other words, I can say in another way we can put, if we move in a direction of electric field, we are moving in a direction of the electric field, potential gradually decreases, or else I can say there is a decrease in potential as we move in the direction of the electric field, and potential increases as we move in a direction opposite to the electric field. So, altogether we get a relation that E is equal to negative potential gradient, that is delta V by delta L. If you substitute this idea, what idea? Idea is nothing but along the direction of the electric field potential decreases, then we can write mathematically delta E is equal to E is equal to delta V by delta L. This is the relation between the electric field and the potential. This normally asks for a 3 marks derivation in the board exam, the relation between the electric field and the potential. So, this is very important. Say if there is an electric field, say here. Now, if I think of the point say A, say think of the point B, think of the point say C, say think of the point D here. If I ask, what is the relation between the potential at these points? If the separation between them, the distance is same, what all the relation you can think of the potential at there? Obviously, the first point is what? First point is the potential at D is lesser than potential at B, which is lesser than the potential at A, and we can write that potential at A is equal to potential at C. Why? Because A and C lie on the equipotential surface. A and C lie on the equipotential surface. D is along the electric field line ahead. So, potential at D is much smaller than the potential at B. Potential B is smaller than the potential at A and potential at C. One more thing, second idea is potential difference. Say if I write potential difference between B and D by delta L is equal to potential difference between the B and A divided by delta L. This is the meaning of what we call the gradient. So, from here to here how much it changes, the change in potential divided by the normal distance is equal to the change in potential from here to here divided by the distance. So, potential gradient is a constant. Why potential gradient is constant? Because the electric field is a uniform one. Electric field is what we have taken is nothing but a uniform electric field. Since there is an uniform electric field, the potential gradient remains a constant. If it is a non-uniform electric field, for a non-uniform electric field, the potential gradient don't remain constant, they keep changing. If the electric field is increasing, gradient will increase. If the electric field is decreasing, gradient will decrease. Based on this relation, electric field is equal to potential gradient delta V by delta L. So, this is an important point to remember.